Okay. Right. So thank you for the invitation to speak here. Yeah, it's been a great conference. I'm happy that I can contribute something to it. So what I'm going to talk about is uh, sort of one approach to defining the genus zero open Gromov-Witten invariants. So some version of this is in a paper that I posted in the summer of 2024, but like the main new thing I want to update you about is just you know that I can prove like now some integrality results for these things in certain cases that I will try to describe. So the setting that I'm going to look at is where I take M omega to be a closed symplectic manifold, and I want L in M to be a closed, maybe spin oriented, connected Lagrangian embedding. Okay. And so like we saw in Tobias's talk, one thing that you see here is that if you try to take naive counts of J holomorphic disks, right, with boundary on L, these are not going to be invariants of the almost complex structure. So they're not. Right. And the main issue that you see here is that if you consider, say, an isolated disk with boundary on a Lagrangian submanifold, you can ask what will happen to it when you try to vary your almost complex structure in a one-dimensional family. And one of the things that can happen is that you can see sort of these disk bubbles forming. So, right. So it'll look something like that. You'll see this kind of nodal configuration, and this is a codimension one phenomenon. So, you can't use a cobordism argument to show that these counts of non-nodal holomorphic disks don't vanish. I should say right now that there's sort of another thing that can happen, which is that if you start with a holomorphic disk with contractible boundary, you can also see bubbles of this form, where like the boundary is contracted as you move in a one-dimensional family. But I'm not I'm not going to address this too much. So the main like algebraic difficulty will be in finding some way of canceling this these disk bubblings, and there are sort of well understood ways in this context for canceling sphere bubbles. So you can restrict to like a null homologous Lagrangian and equip it with like a bounding smooth singular chain or whatever. Or alternatively, you can just not like count disks with contractible boundary, and there's still a way to produce.
Can you have sphere bubbles that bubble out of this?
That's going to be a codimension 2 thing, right? Like in closed Gromov-Witten theory, right? So you don't need to worry about that. Okay, so one approach to handling disk bubbles, which is originally due to Fukaya, and here we're going to restrict to the setting where M is a symplectic Calabi-Yau threefold, and L is Maslov 0, like in Tobias's talk. So in this setting, you can define the Fukaya A-infinity algebra of L, which I'll denote like this, and it consists of the following data. So it has an underlying module, which is given by de Rham, by the de Rham complex of L, and this is going to be with coefficients in the real Novikov field. Right. So it's like the ordinary Drom complex where we take like some completed tensor product of this thing with the Novikov ring. And then you have these operations. Starting with k equals 0. And what you're supposed to think of these as is they're going to be, they're sort of going to be defined by counting holomorphic disks with boundary on your Lagrangian and k+1 boundary marked points. And then another piece of data, which I'm going to include here, is this pairing, which is the Poincare, or like the integration pairing. So what this is that if I have two differential forms in omega star of L, I can, take their wedge product and integrate it, maybe correcting by some cosine sign. And so the reason that we're working with the Drom complex is the following. So there should be some compatibility of this integration pairing with the A-infinity operations, right? So they should be cyclically symmetric, meaning that if I take any k+1 differential forms and I look at the following expression, then up to a cosine sign, I should be able to take cyclic permutations of these inputs, and it should preserve this value. Okay. I'll say a little bit more about this in a second, but once you're given this data, you can define, or you should consider an additional piece of data, which is what I'm going to call M-1 beta. So here beta is a class in the relative second cohomology, M relative to L. And, what I want this to be is, the number of points counted with sign in this, so there's the moduli space of J holomorphic disks in M with boundary on L representing the the class beta in relative second cohomology. So I think as we saw in Tobias's talk again, in the Maslov zero Calabi-Yau threefold setting, this moduli space is going to have virtual dimension 0. So so what Fukaya shows is that you can equip this thing with some Konishi structure, which lets you treat it as a a finite set with an orientation, and so you can count the number of points in it, in some suitable sense. So yes. No. So there's a sense in which I sort of get a weaker invariant than what Echelman and Chende get. I cannot work with non-compact L and M. There's there's essentially has to do with needing some appropriate form of Poincare duality.
Why didn't you have J on the Kaya product?
Sorry, yes, they do.
Do
sorry, they depend on J. It's just a failure of notation. Okay. Okay, so I'll define M-1J to be this weighted count of disks, weighted by some power of the Novikov variable, and then we can define the open Gromov-Witten potential, of L, which is a function, phi, which for me is going to take values in the set of Markov-Cartan elements of L, and it will map to the Novikov field. And right? So this, right, so for the record, this is the set of bounding cochains. For L, modulo gauge equivalence. Right, so you should just like think of this as like something with whose domain is like the set of objects in the Fukaya category, supported by your Lagrangian. Right, and the value of this thing at B is going to be this m-1 term that I defined, plus some higher order correction terms. So right. Okay, so you have so you have something like this. So so we've introduced this like extra piece of data, but there's kind of a slightly simpler way that you can think about the value that you get, which is that since B is a bounding cochain, you can represent it by some closed like degree 1 differential form. Because we're working in dimension 3. Right, so it's closed with respect to the de Rham differential. And then if you're given this, you can produce a local system from B. And produce okay. Right, a local system. Right, X but B. And right. And this thing is going to be given by, or holonomy representation is this. So it's a sum from right. So you just want to right, basically take a class in H lower 1 of your Lagrangian, cap it with cap it with your bounding cochain, and then exponentiate it. And this is this is going to give you a local system. Because we're working in a setting where the Fukaya algebra is nice, this lets us rewrite. Right. This lets us rewrite the open Gromov-Witten potential in terms of local systems. So after all that, we can really say that the open Gromov-Witten invariant is going to be sum over relative cohomology classes, right, with weights in the Novikov variable. Right, like this. So, we have this data defined in terms of like the higher infinity operations, but the invariant that we get is something that can be interpreted as a count of disks with no boundary marked points, but which are weighted by like the holonomy of some local system. Okay, and so if we go back to this picture with disk bubbles, the picture that you should have in mind is that you'll just look at some count of holomorphic disks, which is where the boundaries are like weighted by the holonomy of some local system. And so as you vary J, what's supposed to happen is that whenever you see a disk bubble, it's going to carry some algebraic factor, which is the holonomy of this local system. And the condition of that there's a bounding cochain will tell you that the count of all these teardrops weighted by holonomy vanishes, right? And so that's another way of correcting this the invariance of this thing, but it depends on some data like in the A-infinity algebra. So so yeah. Right. So I guess you could ask why are we not taking something like this to be the definition of our open Gromov-Witten invariance as opposed to this thing which goes through the infinity algebra. So I guess the first technical reason for doing this is that actually making an invariance proof of this kind using local systems is something that's sort of difficult to do. But if you want to work outside of the Calabi-Yau threefold case, this would be kind of a considerable loss of generality. So what I want to say next is that under some regularity assumptions, and replacing the Novikov field with some larger ground ring, Solomon and Tukachinsky, extend the definition of phi to higher dimensions, and M possibly non-Calabi-Yau. Okay, and so the new thing that you're going to see here is that if I think about what a bounding cochain for the algebra of this thing will be, it's no longer going to be represented by a degree 1 form. So you're going to miss out on this correspondence between between local systems and bounding cochains. So that's so that's one reason for doing this. But their work is still going to be, still going to involve using the de Rham complex. So if you just look at, this definition as I've given it, you can, only say that you get like, open Gromov-Witten invariants of your Lagrangian valued in the real numbers, as I was saying before, this is, this has to do with like the chain level model for the A-infinity algebra that we decided to use. And, so you might ask like, what would go wrong if we tried to replace the de Rham complex with something like singular chains or Morse cohomology? And the answer is that we can only achieve, like I guess as far as I know, we currently only know how to achieve cyclic symmetry over the de Rham complex.
What?
Yes.
Is that a math statement?
Sorry?
Is that a math statement?
What do you mean?
That
which statement?
You might be able to assume some sort of cyclic symmetry using some homotopical framework for singular chains, maybe?
I haven't worked this out for singular chains, but I can show you something that that might work.
So you're not saying you cannot do it?
Okay. So up to homotopy, it's a different question. Like up to homotopy, what I'm going to convince you is that the answer is yes, but everything that I've described for you so far has happened at the chain level. So like as I've written it, you'd have to do some work to show that homotopy cyclicity is enough to define these things. I'll just say, where cyclic symmetry is supposed to come from is just the S1 symmetry of a disk, but like when you try to define these domain dependent perturbations that you use to define the higher A-infinity operations, if you want this symmetry to persist, you would have to, perturb them in a way that that respects this symmetry. And the issue is that it's not clear how to do this, while also making sure that the evaluation maps of these moduli spaces at boundary mark points have enough transversality, So there's like kind of a simple dimension counting argument you can do, which shows that you could literally never hope to define like a cyclically symmetric inner product on, say, like singular cochains over L, without using virtual techniques.
But singular cochain. Do you mean singular chains on the base book phase?
I mean singular chains on L.
That's not. You really need singular chain.
If sorry. No, no, I've been using the de Rham complex. Right, so far.
Representations of this algebra.
Right.
Same as the representations of quantized algebra. Chain algebra on the base loops.
Okay. I mean,
If it's not simply connected, you lose some.
right.
Well,
When
by one,
yeah,
right?
that's right.
The sole dual, right?
Yeah, when it doesn't hold, you lose some.
In the chains, if you,
In a simply connected case, you can divide it. If it's non-simply connected, you that's yourself.
Well, yeah. I mean, okay, right. Maybe to say something more, right? Maybe to say something, right, like more naive than this is that you can, right. If you take like singular chains over R or something, then you could, you could, I guess, like try to transfer some like A-infinity structure to that using, right, the de Rham complex, and so, you'd expect a version of, or I guess like something like cyclic symmetry to hold up to homotopy in that sense. Okay. Right. Okay. Right, and so to avoid dealing with some like genuinely difficult transversality issues, right, what I'm actually going to do is to work over the Morse model for the infinity algebra. So I'm going to take the Morse complex of, and at this point I'm dropping the condition that we're working with a Maslov zero Lagrangian and a Calabi-Yau. So I'll work with the Morse complex of L with respect to some Morse function, and I'll define, I'll have some infinity operations like this. So this is some Morse complex, which I'm going to be taking over the Novikov ring with coefficients in a field K. And what MK is going to do now is it's going to count Hurley trees. With K inputs and one output. So it's something like, I guess, what we've seen in Umut's talks. Right, except like all of the vertices of my trees are just going to be labeled by holomorphic disks with marked points and boundary on my Lagrangians, possibly with some, like possibly with some domain-dependent perturbations to achieve transversality. Okay, so so you should now no longer expect to achieve cyclic symmetry on the nose here, right? Because there's just like no cyclic symmetry in the domain, so this is not really reasonable to hope for. But you can show that there is like some homotopical weakening of this. So what you can construct is an A-infinity bimodule quasi-isomorphism. Right, mapping from A to its linear dual. And it consists of the following data. So I'll have a family of linear maps. Right, from tensor powers of A to the dual for integers P and Q, strictly non-negative, and it should satisfy some algebraic restrictions. So I want it to be skew symmetric. Right. What this means is that I can take phi sub KL, and if I take any sequence of inputs like this, then up to a causal sign, I can reverse the order of these inputs. I'll get right. Same thing. The second condition is something called closedness. So if I take any sequence of inputs, right, and any indices I less than j less than k, then I can look at some, sum of some sum of of like permutations of these inputs, which just move like all three of these special indices to be either the bimodule element or the argument in the output, and these should all sum to 0. Okay, and then the last condition is homological non-degeneracy. Right. Right, and I'll just say that what this means is that if I take phi 0, 0, it's going to give me some induced pairing on the on the Morse cohomology of my underlying Lagrangian, and I just want this to give me some non-singular pairing, right? Like actually what I want is for it to give me so like actually for applications to open Gromov-Witten theory, what I want is for this to give me the Poincare duality pairing. Okay, so so I guess the way to think about what these conditions what these conditions give you is that if we restrict ourselves to a field of characteristic 0, then we can construct an appropriate infinity inner product, which is determined up to a quasi-isomorphism of A, by a proper Calabi-Yau structure. Which is phi in the negative cyclic homology of A. And so, and so like when you see this, you should kind of think of this result by Savage-Soyblin, which says that in characteristic 0, maybe if we restrict to unfiltered A-infinity algebras with no curvature, the statement should be that a proper Calabi-Yau A-infinity algebra A has a unique cyclically symmetric inner product. So the naive strategy for trying to define open Gromov-Witten invariants here is that you would like to use some version of this statement. So you're given so if you can show independently that I guess the A-infinity algebra of a Lagrangian always has a Calabi-Yau structure. What you would like to do is to maybe transfer this to some minimal model, and then try to try to mimic the definition of the potential. Okay. And so like again, like one of the reasons that we can't do this directly is that when we actually try to prove that whatever we get is independent of the almost complex structure, we'll have to look at the boundary strata of holomorphic disks with no boundary marked points as we vary J. So if we just pick some like non-explicit like cyclic structure on a minimal model, then then like that we don't really have any hope of getting an invariant. And then the second thing to say about this is that if we are this cyclic structure is sort of not uniquely determined by this class of cyclic cohomology. If we work with a field with positive characteristic. And so I guess like when you go to extract some homotopy cyclic product from this Calabi-Yau structure, there's a way of doing this if you're given a chain level representative for your cohomology class. The problem is that if you try to replace this with some other cohomologous negative cyclic cochain, you would want to compare the inner product. You would want to compare the bimodule quasi-isomorphisms you get on A somehow, and so like the way you would do that is by integrating a vector field in some sense, and the quasi-isomorphism that you get is just going to involve dividing by positive integers. So so if you want any any hope of making this work in positive characteristic, you will want to do something you'll actually want to like pick a chain level representative. And so when I talk about positive characteristic things, that's what I'll actually do. Yes. Yeah. So I'll just so I'll just like say to you okay. So I can tell you what it is right now. So for the Morse cohomology of L, like the Calabi-Yau structure that we're going to get is something which comes from like Ganatra's cyclic open closed map. So you just like take the so you just like take the part of the cyclic open closed map value to top degree, and then this is going to give you the cyclic chain. So that's the model that we're using. He does this construction at the chain level, and we're just going to use that. And this is something that you can show is like well behaved under changing your almost complex structure, but it's like unfortunately not going to be I guess like the open Gromov-Witten invariants that you get are still going to require this specific use of chain that's like not clear to what extent you can improve it. Yeah, that makes sense. So if you want to so I guess if you want a formula for this, you can like look at the formula in like Ganatra's paper and then use the general procedure for producing an infinity or a homotopy cyclic inner product from class. Yeah. Okay. And I guess if you haven't seen these conditions before, like skew skew symmetry, closedness, and homological non-degeneracy are supposed to correspond to properties like this for non-commutative differential forms. So, there's a sense in which you can think of A as some kind of formal symplectic manifold, and this infinity inner product is supposed to be like a symplectic structure on this thing, right? And this, I guess, like where the names of all of these things come from. So in characteristic 0, the statement, this theorem of concentric Schäuble-Mills is supposed to be like a Darboux theorem. So like up to, so like up to some like quasi-equivalence, you can take this, this thing with like higher order terms that you're supposed to think of as like a non-constant symplectic structure and like show that it's like equivalent to the standard one, right? This is this is kind of the idea. And I'll just write down now that in the special case where A is the Lagrangian Floer cohomology, I already said this out loud, but the class phi comes from Ganatra's cyclic open closed map. So given this cohomology class, there's a formula for phi sub pq, which is constructed following Cho-Li, and then there's also a separate way of doing this due to a Mormon too. Okay. Right. And so this is like strictly some algebraic procedure, but I guess just for the record, really this comes from, in the Morse model, this is going to come from counting pseudo-holomorphic Perley trees, which, are going to have some inputs coming from the some inputs coming from the Morse cohomology of L, so from C star of L, and then you're going to have an output disk with like one interior marked point, which is going to connect like a flow line inside L to to some point on to some like Morse generator for your ambient symplectic manifold. And in the central disk, what you're going to have are some like auxiliary interior marked points, these are sort of allowed to vary while being constrained to I guess like concentric circles on this central output disk. So if I have so just to be clear, they still move in a two-dimensional family, so we're not worried about any kind of interior bubbling here, but they're not allowed to move past each other, right? So what Ganatra what Ganatra shows in the monotone setting, and then what I adapt to also the monotone setting, but in the Morse model is that you can make sense of all of this, and this is going to produce for you some appropriate Calabi-Yau structure on the cohomology of L. I guess this is the place at which we're kind of using compactness. If you want to work with some like non-compact Lagrangian, you're not going to get like a proper Calabi-Yau structure, and so there's not really a way of making this strategy work, as far as I'm aware.
Can you use pre-Calabi-Yau?
I haven't worked through. I haven't work through this, but that's, yeah, that's a possibility. Like something else you could try to do is like produce some equivariant version of this if you were interested in like showing multiple cover formulas for the for these open Gromov-Witten invariants or something, but it's not something that I know how to do at present. Okay. So at this point I can show you like the computation that gives you like integrality of these invariants, at this level. So the idea is that if I take this set of of linear operations, I know that it's a map of A-infinity bimodules, so it's going to induce a map on cyclic cochains. So we go from cyclic cochains with coefficients in A to cyclic cochains with values in the linear dual of A. And so what I would like to do is I would just like to take the cyclic cocycle in CC star of A with coefficients in A, and I want to map it to into chains with coefficients in the linear dual under phi sub pq. So it's going to give me something which looks like the sum over all non-negative p, q, and k, like this. If we like restrict ourselves back to the cyclic case, so if we assume, just for simplicity right now, that if phi sub pq is 0 for all pairs pq other than 0, 0, then what we're left with, and here to make this clearer also, just write phi 0, 0 like this, then what I'm going to be left with is a class in cyclic cohomology, or that looks like this. The condition that phi sub 0, 0 was a bimodule isomorphism or quasi-isomorphism is going to tell me that the image of this thing is closed under the B star differential. If all of the higher order terms vanish in a homotopy cyclic inner product, then a computation with like the bimodule relations tells you that what all of these things say is that phi sub 0, 0 is actually cyclically symmetric. So that is if I take like this, if I take like any of the components of this chain and I like cyclically permute all k plus 1 inputs here, then this is going to be preserved with the same cosine sign that we saw before. So you can think of this as saying that this lives in Kansas complex. Okay, so and so if I go back and I give this more general chain with non-trivial higher order terms a name, then by a result of Cho, what we can say is that we can up to quasi-isomorphism replace this replace like any homotopy cyclic inner product with some equivalent cyclic structure up to some I guess like inexplicitly specified quasi-isomorphism of A. So what I've shown in the strictly cyclic case is that this thing is going to be a positive cyclic cocycle, and by this result of Cho, we know that phi prime is also a positive cyclic cocycle. Right, in the non-cyclic case, or in the homotopy cyclic case. Right, okay. And right, at the beginning of the talk, I said that L should be like an embedded connected Lagrangian, and that's going to be used here just to give us some degree, right, just to give us some control over the degree 0 right, the degree 0 cohomology of the Lagrangian. So, you know, right, the fact is that when L is right embedded, so not immersed and connected, there should exist a class eta in the degree 0 negative cyclic cohomology of A with the property that, right, B star of eta is equal to this phi prime. So so the existence of the cycle is kind of given to you completely algebraically, but the geometric picture that you want to have in mind is this. So if we assume that we're in the cyclic case, roughly the way you should think of this is that you want to take disks with an arbitrary number of boundary marked points, and you want to think of all of these as inputs. So if you so if you like do this in the like Calabi-Yau, right, like Calabi-Yau threefold setting, you know, you're going to, right, you would like get something which just like takes in differential one forms and then assigns to it like the number of such curves, right? Just right. So right, this is like a little right. So there's like a little bit imprecise, but this is, you know, kind of the geometric picture that you want to have, and then like it right, like in the Calabi-Yau threefold case, you can actually you know, I don't know. You can like convince yourself that like the cycle that we cook up here inexplicitly is like really given by by something like this. Okay, and so right, this is supposed to be helpful because, you know, now if I, you know, consider what happens when I evaluate this at some bounded cochain, right, I can rewrite this as eta applied to, right, so like the degree k+1 of the part of the cycle is something that I can write as like this. And what this is going to be, right, and what this is going to give me is the sum over all like elements of Z mod k+1 of, you know, the unit in cyclic cohomology tensored with like k+1 powers of B, right? And we can, right, and so we can rewrite this as k+1 times eta of one times b to the power k+1, right? So if you were in it, right, so if you were in a setting where, you know, the infinity operations and this inner product were both, right, were both defined integrally, then I guess, right, by all of these, right, like I guess, but by all of what we've done so far, what you could also say is that eta is also defined over the integers. So I can divide both sides by k+1, right? You know, and right, and what I see here are these like higher order terms in the Gromov-Witten potential, which were not obviously defined over the integers. Okay, so right. Okay, so I guess like you know, from that we have some way of making sense of, right, these like higher order terms in the open Gromov-Witten potential. And so in this statement, I'm going to restrict myself to looking at, I'm going to further restrict myself to looking at a monotone Lagrangian just to avoid any multiple cover problems. But I guess presumably one would expect that if you could set up FOP perturbations for disks with for moduli spaces of disks with boundary on a Lagrangian, then you could I guess define these integer valued invariants in some higher generality. But for monotone L, what I can say is that there is an open Gromov-Witten potential phi, which goes from Mark-Cartan elements on L I'll just say to the Novikov field with coefficients in Q. But this is actually defined over the integers, right? The reason for that is that we can use the definition of the open close map and the infinity operations to say that all of these quantities are actually defined over the integers, but for some I guess technical reasons coming from homological algebra, we want to take things to be officially defined over Q, and then we can show after the fact that that everything is integer valued, and because of some technicalities which have to do with working with filtered A-infinity algebras instead of A-infinity algebras over just a discrete ring, if you to say this carefully, we should say that this phi sub b, this value phi of b has an expression which is given by pairing this negative cyclic cohomology class with some other class called e to the power b, but only up to an additive constant, which we put on to just correct for invariance under changes of almost complex structure. This is like in Fukaya's work. And what I mean by e to the b is that I'm going to look at the sum for all k greater than or equal to 0 of tensor powers of b with the unit in the infinity algebra. So I'll just leave this as a remark, but it's that everything that I was doing so far, we can replace Q with any other field K, possibly positive characteristic. But I just want to point out is that if you take some monotone Lagrangian and you look at its Z or Q valued open Gromov-Witten potential, then you can take the the characteristic P reduction of this, think of it or reduce coefficients to the field with P elements or something. And this is and what I expect is that this should give you a different invariant than reducing from Z to a field with P elements. So so I guess the effect of work of working, like working over the rational numbers, we've lost some information about like torsion and the cohomology of L. But yeah, right. This is just like right. This is just like something that's that I wanted to point out. And then, okay. Right. I see that I'm like running out of time, so let me just finish by, explaining, the title for the talk. So, right, there's this construction by, like Abbaspor, Tradler, and Zanelian in the in the string topology literature, which in the setting of like a non-filtered A-infinity algebra gives us a map of Lie algebras, right, from the negative cyclic cohomology of A with even degree to, like a space of regular functions on the set of Markotan elements of A, just via the construction that's right on the top part of this page. And so, this was compared to some other object, like studied by.
What's A here?
A is an A-infinity algebra.
With no pairing?
No. So, sorry, it should have an infinite. So, yeah, so it should have it should have a homotopy cyclic. Right, so it should have a homotopy cyclic inner product. That's where the Lie algebra structure comes from. You like transfer the you transfer like the cup product on what right okay so there's some other object studied by Abbaspor and Zanelian on the like S1 equivariant homology of the free the free loop space of like some manifolds, which they call the generalized holonomy, and in certain contexts they compare to like a version of this. But the point of all of this is to just say that like even in this setting where we're not assuming that our bounding cochains come from closed differential one forms, you can still interpret whatever this open Gromov-Witten potential is as as taking the holonomy of some local system. Okay. I think I'll like end by saying sort of like one last thing, which should maybe give like some justification for trying to do this over the integers, which is that if you're familiar with Solomon and Tukachinsky's notion of a point-like bounding cochain in this setting, so for a point-like bounding cochain, B, this is in general only going to be defined, over the rational numbers, but you can look at the denominators of of phi of B. Basically, the point of doing all of this was to say that if you take the for a monotone Lagrangian, if you take the open Gromov-Witten invariants defined by Solomon Tukachinsky, the only reason that they'll fail to be integers is for reasons having to do with this choice of bounding cochain. For a real locus, you can get or so for a Lagrangian, which arises as like the set of fixed points of an anti-symplectic involution, you can get some explicit control over what the denominators in Solomon-Tukachinsky's invariants have to be. So, right. So what I want to say is that they give an obstruction to realizing some Lagrangian submanifold as a real locus. And right, and right, I should just say that like contingent on some comparison of my invariants with Solomon-Tukachinsky's, which you can imagine trying to achieve by some like argument using homological perturbation. There are some some examples in the literature where you can like compute or look at known computed values of Solomon-Tukachinsky's open Gromov-Witten invariants, and you can like conclude from like general grounds like this that they cannot be written as real loci. But this is still right. This is still missing some sort of comparison results. But I will stop now. Thank you.